Okay, now let's talk about pressure and what pressure is. Now, the first person to really run into pressure was trying to create a vacuum. First one that really understood something about atmospheric pressure, let's say. And this will maybe help you understand what's going on here. So this person took a long glass tube that's sealed at the bottom, not at the top, filled it with mercury. Chemical symbol for mercury is Hg. And he used this. He tried to create a vacuum doing a lot of different things. For instance, he took it and filled this tube with water, put his finger on the top of it, flipped it over, put it in a tub of water, and he figured that if I turned the tube upside down and it was filled with water, and for the water tried to come out, but I didn't let air in by putting it into a tub, and if I fell down, there would be nothing up there, and I would have what would be called a vacuum, a space where there's no molecules. Well, water's not heavy enough to really make a noticeable drop in it. He ended up putting in heavier stuff, mercury, into the tube, put his finger on it, flipped it over, and put it into a tub of mercury, and the mercury being 14 times as heavy as water, as dense as water, it fell down a ways. And he thought that was pretty cool. I've got a vacuum. But what he also discovered was, as he let this sit for days, this level went up and down. And it took him a while to figure this out, what was going on. And he realized what helped him was that he took it on a trip up into a mountain, and this started going, mountain, that's pressure, fell. And then when he went back down from the mountain, it came back up. And he said, what's going on here? And he's the one that then decided that, there must be air molecules sitting on this tub pushing the mercury up. And if there's less pushing on it, this would fall, and if there was more air pressure on it, it would go up. This would be called the first barometer. And the length of this, if it's mercury, was 30 inches. So sometimes you can hear forecasts, or they're talking about barometric pressure in so many inches, 31 or 2. That means the pressure's high. And to get a high pressure, you have to have heavy air. Heavy air would happen if it's denser, which means it's a cold air mass sitting on there. And cold air masses cause kind of clearer weather. And so when this was going up, then be nicer weather. If it was a warm air mass, which tends to circulate, a lot of air rising and then turning into rain or whatever, this would drop. And so when it dropped, he knew there was going to be bad weather. When it went up, he knew good weather, sort of, roughly. If you did this in the metric system, this is about 760 millimeters, which became 760 millibars. So if you get the atmospheric pressure in millibars, it's just how many millimeters this mercury would be. Why I'm talking about this is we are in a pool of air. Air is stacked up on top of us around the earth. All this air is pushing down and creating pressure on it. And if you were in Europe, the amount of air pressure at sea level is 1 atmosphere. So there's a unit called atmospheres. Well, I'm not going to worry too much about the pressure of the air, but I'm going to be, and as you went up higher, there'd be less air sitting on it, and there'd be less atmospheric pressure, and that's how some of the first altimeters worked. They measured the change in the pressure and said, okay, you must be at such a height. Well, just as you drop further and deeper into air, the pressure goes up because there's more air sitting on top of you. What we're going to talk about is what happens if you go deeper into water. So if I have a pipe, let's say it's 10 feet tall, filled with water, sealed bottom, and put a pressure gauge at the bottom, or I had a big dam on a lake that happened to be 10 feet tall, and I drilled a hole through the bottom and put a pressure gauge. Since it only depends on how deep you are, how much water is stacked on top of you, it doesn't matter if it's a small column of water sitting on top of you or all the water behind the dam. It's still just the depth that controls it. And these two pressure gauges measure the same. The pressure at different depths depend on the weight of the liquid, the weight density of the liquid, and in the English system, the weight density is 62.4 pounds per cubic foot. So the pressure at the bottom of this at 10 feet is 62.4 pounds per cubic foot times how deep I am, times 10 feet. So the pressure there will be 10 times 62.4, or 624 pounds for every foot squared. Now you may be used to not pressure in pounds per square feet, but maybe pounds per square inch. So to convert this to pounds to square inch, I would have to convert square feet to square inches, PSI. So I would have to multiply by feet squared, inches squared, the conversion factor here. So how many square inches are in square foot, or how many square foot in square? Oh, there's 12 by 12 is a square foot. So that'd be 144, 12 times 12. 144 square inches make 1 square foot. So if I cancel these, I would have the PSI at 10 feet. And so 624, where's my calculator? Over here. Got to get this figured out. Where is it? There it is. $624 divided by 144 is 4.33. 4 and 1, 624, 62.4 divided by 144. 4.33 PSI, pounds per square inch. Now, you know, no big deal to you, but 10 feet I pick up 4 pounds of pressure. Now, when I was building my irrigation system, there's a canal up by the road I live by, and I ran a pipe down to my place, which is 80 feet lower. What would be the pressure in the pipe? Is it enough to run my sprinklers? Well, water doesn't matter whether it's this than this, it's how much fall it has. 4.33 pounds per square inch for every 10 feet. So I'd have to take that times 8, and I get about 35 PSI. Would that run my sprinklers? Well, sprinklers like to run at about 60 PSI. So if I don't have a pump on, increasing the pressure, my sprinklers would be pretty lame looking out there. That's an example of using that. Okay, so now, how are we going to use this? All right, so let's just make a tank. Put some water in it. And let's say that it is, let's make it 8 feet tall, 10 feet across, and 12 feet this way. And I ask, what's the pressure on this side of the tank if it's filled up with 6 feet of water? How much force is on that end? So I know how strong I have to make it. Okay? So I'm trying to figure out how much force is on this end. Well, the pressure at the top is not the same as the pressure at the bottom. It depends on how deep I am, how much the pressure is. Okay? So, I start doing my calculus. I make a slice here that has some area, and it's going to be down some depth, and I have to set up a coordinate system, so I have to decide where I want to put my X and Y. It really doesn't matter if I put 0 at the top or at the slice or at the bottom. I'll just do it at the bottom for this problem. And it doesn't matter, since this is uniform, it doesn't matter if I put it in the center or the side. So I'm going to draw my x-axis here, my y-axis here. And so then the thickness of this, the width of this deal, I'm not doing a box. I'm not trying to find a volume. I just want to know the area that the pressure is pushing on. Remember, pressure is a force times an area. Okay? So the pressure at this depth, let's see, if this is y, the depth here, this is the y-axis, and this is the origin, this is y. What's this depth? Well, this is 8 feet up here. So it's 8 feet from here to here, and this is y that's taken away from the 8 feet. The depth would be 8 minus y. That's how far down this is. So the pressure at that depth, since I'm in the feet, the pressure is going to be 62.4 pounds per feet cubed times the depth, which is going to be from the surface down to there, is going to be the 8 feet to the bottom minus the distance up, 8 minus y, and that will be in feet. And so one of the feet cancel, and I get feet squared, so I get pounds per square foot. That's a pressure unit. And the pressure, if I take that times the area that the pressure is pushing on, which will be dy high and 10 feet across, 10 feet times dy feet. The feet and the feet will cancel the other 2 feet, and I'll just get a force in pounds that the water is pushing on this rectangle. And I'm going to then add up the pressure on this rectangle and all the rectangles on this side, all the way from the bottom to the top, to find out how much pressure is on there. So y is going to go from 0 up to 8. That's going to be 10 foot by dy, that's the area, times the force in pounds per area, and that'll end up being a pressure in pounds, the force of pounds. How hard it's the force on that wall. How hard is it trying to push that out? And this is a dy, and that's in y, so all my that works, and I can plug this into my calculator and figure out the force on the end of the tank. Okay, now let's do for a dam. Let's say the dam was 20, no, let's make it, let's do kind of what I did. 50 meters and 80 meters across up here. That's a really big dam. And it's 30 meters high. So now I'm doing metric system, so I'm going to have to do weight density in the metric system. But I'm going to take a slice, and to know what I'm going to call the dimensions of this, I need to put a coordinate system. And this one, it's convenient to put it down the center because of the symmetry for the y-axis. And the x-axis, or the x-axis, I could put it at the top. Let's do it at the top this time, just to see how this works. Okay, so now the dimensions of the slice is dy times, if this is y and this is x, this is over x. So the area of this slice is going to be 2x across dy high. The area times the weight density, which is going to be 9800 newtons per meter cubed. This is going to be, x is going to be in meters, the dy is going to be in meters, so that'll cancel two of them. I need to cancel one more, and that's going to be canceled by how deep that slice is. And the depth of that slice is going to be, since I put my x-axis here, this will be just y, and it'll be pretty easy to do. So that would be left with, this would be meters, meters, meters. That's going to cancel that, and it'll be just newtons of force. How much it's pushing this tiny area, this slice of area, pushing on the dam. Well, I want to do all the slices from the bottom of the dam to the top, and so I'd integrate this, or from the top to the bottom, either way, y being 0 to 30 meters. And that would be the integral, and it would be all fine, except that we got dy, we have a y, that's great, but we got an x. We got to remove the x from the equation. And x depends on how deep we are. It gets bigger up here and smaller down. So one way to get to that is just to, since I've got a coordinate system on here, let's figure out what this coordinates of that point are. Well, the y is 0, and the x is, since I put it in the middle, it's out 40. So it's 40, 0. And if I put this at the bottom, it's the x would be over 25, and the y would be down 30. That's this point. And x is controlled by this line, so I want an equation of that line. So my change in y, well, I go from 0 to 30, that's 30, over my change in x, that goes from 40 to 25, that's minus 15, so that's minus 2. See, I've got my positive y down here, not up here. That's why I called it 23 30 down. So I've got a slope. This is, if I put y up here, I could call this negative 30, and then this would be negative 30. That would change the signs of everything. But I'm going to do it the way I've got it. So the slope is negative 2. Negative 2, if you think about it this way, negative 2 slope. The y-intercept would be up here, a positive number. We've got to figure negative 2x, y equals negative 2x. Then it has to go through, say 40 to get 0. So negative 2 times 40 is 80. It would have to be plus 80 to get 0. So I use this point to figure out the equation. I needed to replace the x because it was dy, so I need to solve for x in this. So I'll subtract 80 equals minus 2x, divide by minus 2. That's what I would use in place of the x. And so I'd have 2 times this, it'd be nice, the 2's are going to kind of cancel, times 980 times y dy, 0 to 30, and I can figure out how many newtons of force are pushing, trying to move that dam out of the way. The total force on the dam from the water. Notice we didn't have to consider at all how far the water's being backed up. That doesn't control anything. It's how deep it is that's important on how much pressure on the dam. Okay, well that's enough for tonight.